Hello, it's Keith here, and this is the fifth in my TMS9900 assembly programming tutorials. This is going to be the last one in which we cover the processor itself, because hopefully we're going to go over really the last of the major commands today. We are going to then continue. We're going to be doing some tutorials on the TI-99 itself. We're going to learn about that hardware. So if you're a TMS9900 fan, you know, there's still a bit more to see. And there may be one catch-up lesson later on because there's some special commands relating to addressing hardware that aren't covered at this stage. Today we're going to be looking at bit operations. We're going to be doing bit shifts, compares, the AND or XOR type commands, although they're a little bit different on the TMS9900, but we're going to go into all of that with practical examples as always. Let's go over to today's code and let's see what we'll be looking at. Okay. So here's today's example, and we're going to be starting with bit shifts. Now, like most of these kind of processors, we have some fairly common commands. We've got rotation commands, which will rotate around within a register. Of course, all the registers are 16-bit. Now, first of all, we're going to look at the command SRC, which stands for Shift Right Circular. Now, this is the equivalent of an ROR command where the bits shift around within the register without using the carry. Now, let's fire this up and let's see what happens. Okay, here it is. So if I just run this, you can see we've got a starting value here, and we're shifting by 1 bit each time to the right. So in this case, the 1 bit here has been pushed out here, and it's reappeared over here. And then this 0 has been pushed out here, and it's appeared here. Each bit you can see is moving 1 each time here to the right of the screen, because the shift right circular. So as I say, the circular part refers to it repeating around, so you can see that eventually we ended up exactly in the same place as we started after a total of 16 iterations. Now, we don't have a shift left circular, but we don't just need to shift by 1 bit each time. You can see here we can shift by 2 bits, and that will work exactly the same. You can see that's worked just fine. And of course, there's no limit to this, so we can actually shift by a total of 15. And if we look at the result of shifting right 15 times, well, we can see we've actually effectively shifted to the left by 1. So although there's no shift left circular, shift right circular with a 15 or 14 if you wanted to shift left by 2 will have the exact same effect. So we don't actually need a left at all, which is quite handy. Okay, so that's our rotate command. We have also a logical shift. Now, if you're not familiar with it, there are 2 kinds of shifting for mathematical values. Shift arithmetic, which is for signed numbers, and will make sure that a negative number remains negative, because if we're shifting to the left, we're effectively doubling a number, but if we're shifting to the right, we're effectively halving it. But if we shift to the right and the sign changes, then the number would become invalid if it's considered a signed number. So we have these logical operations which are designed for unsigned, and arithmetic operations which are designed for signed numbers. And we'll be seeing that now. Now we're going to shift to the right logically first, and we'll see the result of this. Now this time the bits will not rotate, so if we just run this here, well, you can see the bits have been shifted to the right. You can see that this starting bit is shifted 1 each time, but the new bits aren't being taken from the carry or the bits on the left here. They're actually being filled with zeros here. Now, why are they being filled with zeros? Well, because this is logical, and this is effectively halving an unsigned number here each time we do this. Now, if we were wanting to deal with a signed number, we don't want to use the logical version, we want to use the arithmetic version. And you can see here, that's running here. Now, because the top bit was 1 here in this case, all of the new bits that are being inserted are also 1 here. Now, that's not given. The new top bit is effectively whatever the previous top bit was. So if I change this to a 0 here and I run again, well, now you can see, even though it's the same command, the top bits are now all being set to 0 because the top bit was originally 0. So, as I say, it's effectively sort of dragging whatever the top bit was and filling all new top bits with that original top bit, and that effectively maintains the sign while halving the number. So that's quite handy there. Now, because these are not rotating around, we can't just use the right shift with a value of 15 like we did with the right circular. So we actually have a left shift command here. We have shift left arithmetic, and if we run this, you will see that this will shift all of the bits to the left, and unlike the other one, this will always put new zeros in, because this is effectively doubling the value in the register, provided no bits get pushed out, but if they do, then there's really very little we can do about that. So you can see here that this is shifting the bits to the left, and any new bits are 0 here. And it doesn't matter what the top or bottom bit were, new values are always going to be 0. So that's shift left arithmetic, but it would also effectively be shift left logical as well. There's no need for shift left logical in this case, so there isn't one. So SLA is effectively also SLL here for the logical left shift. As I say, those can all work at any value. I've just used one here as a sort of simple test. It's not a requirement. We can use any size we want. So there we go. So that's those commands. Now, those are the shifting commands available to us. Of course, we do have a variety of operations for changing registers at the bit level, and we're going to be looking at those now. Let's have a look at them. Okay, so we've got a set of test values here, very interesting, and we've got a mask here, and we're going to use this mask for some of our operations here. Okay, so we've got a value 1, 2, 3, 4, and our first option we've used here is the invert command here. What's invert do? Well, it simply flips all of the bits. So effectively the bits within these registers have been changed from a 1 to a 0 and a 0 to a 1. And you can see that here. So this has gone from 1, 2, 3, 4 to EDBC here. And actually I will just add another command here. If I just put this in again, just as a quick test here. Well, you can see if we invert those bits again, we go back to 1, 2, 3, 4 here. So that's just flip the bits there. Now, we've also got a neg command, which will convert a positive to a negative or negative to a positive. Well, what's the mathematical command that does that? Well, I think maybe we've discussed it before in this tutorial. What we have to do is we have to flip all of the bits, and then we have to add 1. So effectively, neg is almost the same as inv, it's just adds 1 afterwards. And you can see that's happened just here. So 1, 2, 3, 4 inverted was EDCB. Well, if we add 1 to EDCB, we would end up with EDCC. And you can see that just here. And again, if we negate a negated register, we'll end up with the starting value again. We're back to 1, 2, 3, 4 there. So that's the neg command. Now, as well as the inv command, which flips all of the bits, we can use the XOR command, which will use one register and flip the bits where the bits are 1 in the parameter in the destination register. So we've used FF here. And so that has flipped the bottom half of this register. So the 1, 2 is unchanged because those bits were 0. And the 3, 4, those bits were 1 in this FF. So they've been flipped. So you can see we've got the CB in the same way as we did here. But the top half is still 1, 2 because those bits were unchanged. And of course, yeah, we can use any value we want in that register and the effect will be similar. So if I just change that to just an F there. Well, now you can see that the 1, 2, 3 is unchanged, but the 4 has been flipped there. So that's what those commands do. So a variety of useful commands there for us. Now the other command that's quite handy is going to be absolute. Well, what's absolute do? Well, you may know that one. Absolute will convert a negative number to a positive number, but it will leave a positive number unchanged. So here we've got 1, 2, 3, 4 here. We flip the bits. And that became this number here. Now, because that's not really a negative number, it's just inverted, when we convert that with absolute, we end up with 1, 2, 3, 5, because as I say, we should have added 1 when after flipping the bits if we wanted a negative number. So we've actually ended up with 1, 2, 3, 5 there. Now, 1, 2, 3, 4 negated is EDCC. Now, that's a negative equivalent of 1, 2, 3, 4, so that's minus 1, 2, 3, 4. So when we absolute that, we end up with plus 1, 2, 3, 4 here. Now, 1, 2, CB here is actually a positive number, so abs doesn't change that in any way, and you can see here this 00FF is also unchanged by the abs. But if I just change that 00FF to FFFF, you'll see, well, now that's effectively plus 1 when that's been abs, because that's minus 1 there. So yeah, that abs command will convert a negative to a positive. Those are the next set of commands we're going to be looking at. Now, in my other tutorials, we've always looked at things like AND and OR at this stage. Unfortunately, they're a little bit tricky on this processor because, like the PDP-11, back in those days, it seems that AND wasn't necessarily quite the same as it is today. Now, with the TMS9900, we have an immediate AND and an immediate OR. These are AND-I and OR-I, and what they do is probably pretty logical, hopefully. So these are using an immediate value and a register here. So you can see we're ANDing 0FFF here with R0 here. And so you can see effectively that where the bits are 1, the value is retained. Where the bits are 0, the value has been changed to a 0 here. So this has effectively lost that 1 because its bit was 0 here. Now the OR I command is again very logical. What it effectively does is it will set to 1 any bits in the parameter that are 1, but any bits that are 0 are unchanged. So in that case, the 1 has been left unchanged, whereas these bottom bits have all been set to 1. Now we've been doing those tests with some hexadecimal values here, and these are all Fs and zeros, which is not necessarily the clearest for showing the flexibility of these if you're not familiar with them. Of course we can use any values here, so we could use 1 FFE here if we just run that. Well, now you can see that effectively the same kind of thing has happened here. This time all of the bits here have been retained okay, but this time we've set this bit here as well because of this 1 here, and this has now become an E because of this E here. So as I say, these, although we're looking at them in hexadecimal, are working at the bit level. Now with these commands we've been looking at immediate values, and that's all pretty straightforward, but we would, and other processors have an AND and an OR that would work with registers combined. Now in this case we sort of have an OR, but the name is different. We don't quite have an AND, so what we have is SOC, which means set ones corresponding. So where the parameter has a 1, the destination will have a 1 set as well. Now SZC is set zeros corresponding, and this is basically saying where there's a 1 in the parameter, the destination will have a 0 put in, so it's effectively the reverse of an AND. So if we took our parameter we wanted to AND, we flip the bits with the invert command, and then we use this command, it would have the effect that we would typically expect from an AND. So let's have a look at this here. So we're using this value here in R5 here, which is the same value we tested originally here. So if I just reset things here just so we can compare, okay. So you can see here we've used our parameter here, and we've done the set ones corresponding with R5, which is this value here, and we've done that to R2. So you can see these bits have all been set to 1 here, and this has become FF. Now when we did the set zeros corresponding, the bits that are 1 here are now set to 0, and so this is, as I say, the reverse of an AND, because this would be the equivalent of doing an AND with F and then zeros here. I'll just prove that to you here. If I just put in the equivalent of the reverse of that R5 value here, well, you can see here now that R0 and R3 have the same value, because, as I say, the zeros corresponding is effectively the opposite. It's effectively an AND with the opposite parameter, the inverted parameter. And I can show you that in a different way as well if we want. If I just do an inv of R5 here and run again, well, now you can see that our AND I parameter result and our set 0 corresponding with that inverted R5 are now the same value here. So as I say, it's a bit of a shock for someone coming from the Z80, but it seems that set zeros corresponding, sets 1 corresponding were kind of the way things were being done back in the days of the PDP-11 and the TMS9900. They make perfect sense. They're just surprising to someone who's not used to them, is the way I feel about them. So anyway, that's what we have. So that's what we need to look at here. Now with the TMS9900, as well as these word-based commands, we do have byte-based commands as well here. So in this case we have a set ones corresponding byte and a set zeros corresponding byte as well here that we can use. So if we just run these, well, you can see that these have worked at the byte level here, and it's only this top byte that have been affected, even though the value in the register would have potentially affected more if we hadn't used these byte-based commands. If we use these word-based commands here, run again, well, now you can see that this nibble of the low byte has been affected as well. And as I said before in the previous lesson, these byte-based commands on the TMS9900 are a bit odd, because the byte-based commands use the top half of the register, whereas on every other system they'd use the bottom one. But that's just the way these things work. Now, as well as the set ones and set zeros corresponding, we do have some test commands which are quite curious. We can do a compare ones corresponding or a compare 0 corresponding, and the flags will be set accordingly depending on how things compare. So let's take a look at these now. So we've got some test registers here, and we're going to be changing them, and we're going to be doing a comparison here. So we're testing R0 here, and we're going to do a compare ones corresponding here, and the one you want to look at is the 0 flag here. Now in this first example, all the bits that are 1 in R1 are also 1 in R0 here, so the 0 flag has been set because the two match. Now when we shifted here, the ones were no longer all matching, because you can see this 0 does not match this 1 here, so the 0 flag was not set, and we've shifted along accordingly here, and you can see that it's only when all the ones in this parameter here match in this parameter here that we get that equals flag set. But however, please notice that these two registers don't match. It's only the ones that match, so the ones in this one matched the ones in this one. The ones here weren't looked at because those values were 0 here in this register. So that's how compare ones corresponding works. Now compare zeros corresponding is basically the opposite. What it will say is when the value in R1 is a 1 at the bit level, is the value in R0 a 0 at that position. So here we're checking if all of these bits are 0 in R0, and of course they are, so the equals flag set. But then we test here and they're not. We test here and they're not, and basically they aren't again until we get to this point here. Now this is of course a different value here. We're testing an 8, and again it's just to make the point that it's only the bits that are 1 here that are being tested in this register here in R0. So the fact that there was another bit 0 here that was not tested because we didn't have an F here, we had just an 8, doesn't matter. It's the fact that the bit that was tested was 0, and the bits that are 0 in this test register are ignored in the value being tested here. So you can see that we're setting the flags here, and so this is our sort of bit comparison operation. It's a little bit tricky, as I say. I find it quite confusing, but that's because I'm not used to this kind of processor. I'm more of a Z80 person with some 6502 experience. But as I say, I find it really quite interesting to see the way things worked differently on this processor, and while I sometimes struggle with it a little bit, I don't consider that to be a failing of the processor. I just find it to be a failing of the things I'm used to and not being able to adapt to a different, perfectly valid way of doing things. So there we go. So that's all we're going to be covering for this point at the processor. As I say, there are a few other commands relating to accessing hardware, and we'll probably do a catch-up lesson later on when they become relevant. The reason we're not doing them at this stage is because, to be honest, I didn't get to need them until I started playing around with the joystick of the TI-99. So for the basic stuff of learning the processor and getting the graphics working, you don't need them. So we're not going to cover them at this stage, but we probably will come and do some catch-up later on. Anyway, though, I hope you've enjoyed this lesson. If you have, please like and subscribe. If you like the video, then it helps with the Google Analytics. And if you subscribe, it gives me a little bit of encouragement to keep working on it, because these tutorials take quite a lot of time to write, as you might be able to imagine. Anyway, though, whatever you do, I hope you've enjoyed this tutorial series. I hope you're going to have fun with the programming. If you've never seen this processor before, I hope you've enjoyed it as much as I have. Whatever you do, though, take care of yourselves. Thanks for watching, and goodbye.